In section 3.7, we're going to discuss related rates problems. So I'm kind of really bummed that I didn't bring in a nice demonstration today. I have one that I like to bring in, but maybe we'll do it on Thursday. In any case, what I want you to do to start things is picture a balloon, blowing up a balloon. As you're blowing into that balloon, what kind of things are changing? Volume, pressure, surface area, radius. So there's a lot of things that are changing all at once. And the way those things change together makes it a related rates type problem. You're going to be calculating how one rate, like the rate of change of volume, is related to the rate of change of the radius, etc. Now we're going to start these types of problems with problem number 4, which is void of any real applications here. It's just to try and get you comfortable with these types of problems. They give us an equation, x squared plus y squared equals 25. And they also give us some information. They tell us that x equals 3, y equals 4, and dy by dx, or excuse me, dy by dt, very important, dy by dt is 8. Now they ask you to find dx by dt. And I want you to notice something in particular about this problem. We're not differentiating with respect to x. What are we differentiating with respect to? T. We're differentiating with respect to t in both of these things. So that's going to be common to all your related rates problems, is you're not going to differentiate this with respect to time, or not with respect to x, but with respect to t, with respect to time. So let's rewrite this a little bit as x squared plus y squared equals 25, and then take its derivative with respect to t. Now let's be careful. We're not differentiating with respect to x like we're used to. We're differentiating with respect to t. So as I take this derivative here, I have to apply the chain rule. It's the derivative of the outside times the derivative of the inside. So what's the derivative of the outside? 2x to the first power, which I probably shouldn't write to the first power, times what? Times the derivative of the inside. Now if you're differentiating with respect to t, that's going to give you a dx by dt on the inside. How about the second term? Amelia, what are we going to get when you differentiate the second term? dy by dt. Yeah, we're differentiating with respect to t in this one. Equals what? 0. Now you could solve for dx dt, and that's fine. Let's just plug in what we know and see where we go from there, because we know a lot of these values. You're going to get 2 times 3 times dx dt, which we don't know, plus 2 times y, which is 4, times dy dt, which is 8, equals 0. But after we substitute in our knowns, the only unknown is dx dt. So I get 6 dx dt. Did I substitute these right? Did I get them back? Okay. Yeah, 6 dx dt equals what, 64? Negative 64. Yeah, negative 64. So divide by 6. I get negative 64 over 6, or better yet, negative 32 over 3. And that's your dx dt. So, given all the information, this is how x is changing. Okay. Let's look at our handout. So I think we've got a nice little rendering here for the second one. We're going to start getting into the applied problems. Now, some of these formulas I expect you to know, some of them I don't. I'm not sure I really expect that most people have the volume formula for a sphere memorized. In case you do, or in case you don't, here it is. Volume of a sphere is 4/3 pi r cubed. So, okay, nice. Let's look at problem 14 and see what it gives us. So it says, a spherical balloon is inflated with gas at a rate of 800 cubic centimeters per minute. How fast is the radius of the balloon increasing at the instance the radius is A, 30 centimeters, and B, 60 centimeters? So let's take a look at some of the things that they're telling us here. In particular, what should catch your attention is this idea of rate. Spherical balloon is inflated with gas at a rate of 800 cubic centimeters per minute. Is there any way I can characterize that rate? Can someone come up with some notation for us there? dV by dt. You're changing the volume is what you're doing. So dV by dt equals 800 cubic centimeters per minute. All right, so let's write that down. dV by dt equals 800 cm cubed per minute. Okay. Then what? Well, there's a part A and a part B. Part A, we want to find out how fast the radius is changing when it's 30 centimeters. And part B is when r equals 60 centimeters. But looking at my formula, I don't have any place to plug in for a dV by dt. And it seems like what I need is dr by dt, the rate of change of radius with respect to time. So yeah, let's find the derivative. Basically what that means is we're going to have to differentiate this relationship, d by dt, with respect to time. So let's treat both of these as being kind of special, because you can't just differentiate this and get, say, for instance, 3r squared. That's not right. What's the derivative with respect to time for this equation? Liam? Well, this is just a constant, so let's just focus in on differentiating this, and then we'll clean it up later. All right, derivative of the outside is 3r squared. Good. That's the derivative of the outside times the derivative of the inside, dr by dt. And I hope by writing it in those brackets like this, it reminds you to differentiate these things implicitly. Let me say this as bluntly as I can. If you're doing a problem from this section without differentiating implicitly, it's wrong. It's just, I can grade it now, you're going to get a 0. It's wrong. You have to differentiate implicitly when you're working these problems. Now the 3 and the 3 cancel, so we get dV by dt equals 4 pi r squared dr by dt. Yay. All right, I think I've gotten down to the point that I can actually do some solving here. So let's work on that. Yes? Yeah, I guess you could think of it using it. Well, there's a 1 right there, so it'd be derivative of the outside would be 1 times v to the 0 power, and v to the 0 power would be a 1, times the derivative of the inside. And the derivative of the inside is really what I wrote there. So, yeah, I guess you could think of there as being an invisible 1. Sure. Let's do part A here. So for part A, we've got dV by dt is 800. 4 pi r squared times dr by dt. So on the right-hand side, that's 3,600. Let's see, 900 times 4, yeah, 3,600. Let's see, 3,600 pi dr by dt. If we divide both sides by 3,600 pi, that's going to simplify to 2 over 9 times pi equals dr by dt. Let's keep in mind something about dr by dt. R represents what in this problem? Radius. So how many dimensions in the radius? It was just one, right? It's just one. It's just the length. So the units should reflect one dimension. Now we started out in centimeters, so we're going to continue in centimeters. Centimeters, but keep in mind this is going to be a rate. So it'll be centimeters per minute. Yeah, centimeters per minute. So overall, you should end up with 2 pi over 9 centimeters per minute. Now, I'm not going to take the time to do it, but I'll give you the answer to part B. But let's think a little bit. As you blow up a balloon, what happens to the rate of change of the radius? Does it start out fast and slow down, or does it start out slow and then speed up? What happens as you add more air to the balloon? Yeah, it starts out fast and it's going to slow down. So you would expect that if you put in, say, 60, you should see an even smaller rate of change with respect to time. So this is part A. For part B, if you solve for dr by dt, you're going to get 1 over 18 pi centimeters per minute. So basically, you double the radius. The rate of change goes down by a factor of 1/4. So that does kind of match our expectations here. And to check that, all you have to do is go back and plug in R is 60 here. Okay. Let's try a couple more problems. There's 3 more problems I want to get through. 18, 20, and then maybe a Pythagorean theorem type problem. But we're going to move over to problem number 18 next. Are we okay with 14? So 14 is kind of a nice intro to some of this stuff. Let's keep going with problem number 18. Okay. Problem number 18. Again, you're going to be presented with a geometric figure we're going to have to work with. A cone in this case. The volume of a cone is not an expression that I expect you to know. I'll give you that on an exam. So what we're going to have to do is work with it. This one's going to result in similar triangles. So let's see what we got for problem number 18. A canonical tank. Vertex down is 10 feet across the top and 12 feet deep. Water is flowing into the tank at a rate of 10 cubic feet per minute. Whoops. There we go. Water is flowing into the tank at a rate of 10 cubic feet per minute. Let's stop there for a second. Can somebody characterize that for me? What is that telling me about my problem? Perfect. Thank you. dV by dt, the rate of change of the volume, is 10 cubic feet per minute. Find the rate of change of the depth of the water when the water is 8 feet deep. So, a lot going on here. Let's write down a few things that we know and a few things that we don't know. So we'll start with some of the stuff that we know. dV by dt is 10 cubic feet. What was it, per minute? Yeah. Per second would be an awful lot. And let's see, they told us the height here, right? What's the height? That was 12 feet. What can I label this side with, the radius with? 5, good. So r equals 5. All right, so we got r is 5 feet. What are we looking for? We're looking for the rate of change of the depth. And another name for depth here, I'm going to call it the height. So we're looking for dH by dt. And we're looking for that at a particular instant of time. We're looking for that when the water is 8 feet deep. So when h is 8. Okay, let's plug some things in and see what we can come up with. Now, one of the things I want to avoid, you can kind of see right here. In order to solve a related rates problem, you're going to need to differentiate implicitly. And right now, differentiating implicitly would involve the product rule, because both r and h are functions of time. The radius changes as you add more water, so does the height change. So it'd be nice to get rid of one of those. So let's do that. And the way you do that is with similar triangles. Let's start out with kind of the big one here. Right here. This outside triangle. That's going to be similar to a smaller triangle at some unspecified height here. So when you have a height up here, something like that, then you have two similar triangles. Both these triangles have the same angles, but different length sides. That's okay. Let's call this our height and this our radius. How does similar triangles help us? Well, the ratio of their sides has to be the same. So for instance, 12 feet is the height of this big triangle. 12 feet over h would be the same as 5 over what? 5 over r. Let's cross multiply here. This is a proportion. So I get 12r equals 5h. And now I want to think carefully about which one I'm going to solve for. Well, eventually, I'm going to answer questions about dH by dt. So I want to leave h in the problem. It means it'd be nice to get rid of r. So in other words, r is 5 over 12 times h. And what we're going to do is we're going to put that into my volume formula and see if we can't get some simplification. So I'll take that expression, plug it into my volume formula. 12 squared is 144, times 3 is 432. So I'll have 25 pi over 432 h cubed is v. Whew. All right. Well, we're getting closer. We're getting closer. How are we going to solve, or what are we going to do next from here? Good. Differentiate with respect to what? Good. With respect to t. So let's find dt on both sides. d by dt. I'll do the left-hand side here for you. That's just dv dt. See if you can't clean up the right-hand side a little bit. $432. Good question. Is this a quotient rule problem? No. Basically, this is just a big constant, right? All you have to do is differentiate h cubed. So I'll leave the 25 here. Well, let's see. Let's just do this. What's the derivative of h cubed with respect to t? So let me just write it here. 25 pi over 432 times 3h squared. Is that enough? dh dt. If you want to write h prime, that's fine too. You know, most people don't do this. The 3 does cancel into here. Leaves you with 144. Most people multiply and get 75 pi. We'll do it that way. 75 pi over 432 h squared dh dt is dv by dt. We know h, and we know dv by dt. So let's finish solving here. Let me go over here. dv by dt was 10. 75 pi over 432 times h. H was what, 8? Times 8 squared times dh by dt. So that's going to be 64 times 75. What's that? 4,800. Someone bang that out on a calculator for me. So 10 equals 4,800 pi over 432 times dh dt. If you multiply both sides by the reciprocal, 432 times 10 is going to be 4,320 divided by 4,800 pi is going to be dh by dt. I should leave room for some units. dh by dt. Eight was the depth of the water. They told that to you in the problem. So probably should have listed that over here, like h equals 8 feet. Speaking of units, though, what units go here for this? Feet per minute. Yes, feet per minute. Good. Why is there no cube or squared? The depth just has one dimension, right? It's just the length. So, cool. Anything else on problem number 14 here? How many problems? No more than 8 or 10. Seriously, limited. At most. Yeah. No, I keep it reasonable. If you look back at my old exams online, I think you'll see that I keep it reasonable. I understand these problems are challenging. I put some on there because we cover them in class. They're important applications. But it's not going to be the whole test. It's going to be reasonable. Justin? 4,320 over 4,800 pi feet per minute. Because you have to multiply by the reciprocal of this on both sides to get it off of the right-hand side. So I don't really have much room for the reciprocal in here. I just kind of remind you that it would be multiplying by 432 over 4,800 pi. So on the right-hand side, those will cancel. And on the left-hand side, you get 10 times 432. Okay. And yeah, that you could reduce that in lowest terms. I don't care. I just looking for a decimal value at that point would be fine. Yes?
From the equation itself and from the word itself, how do you find dH over dt? How do you know it's dH over dt?
Because they're looking for the change in the depth.
Okay.
So the depth would be equivalent to the height.
The next one is 12 over h equals to 5 over r. I zoomed out on that one.
One more time? What was
12
that?
over h equals 5 over r.
Okay, so we're using similar triangles here. 12 is the height of this big triangle, the yellow one. H is the height of this general one here. So I'm trying to establish a relationship between H, R, and 12 and 5. So this side to this side would be the same as this side to this side. Those two ratios have to be the same because the triangles are similar. The only difference is that one has been stretched bigger than the others. So there's scaled versions of each other. You could have set it up in different ways. I mean, a lot of different ways. But, you know, I like keeping it pretty straightforward, like to like. All right. Actually, I should have taken out my calculator. Just as a reminder, you can take out your calculator. You can divide this. I wouldn't put in the pi, but after you divide that, then you can see that, oh, okay, that's really 9/10. So I could write this as 9 over 10 pi, and again, the units would be feet per minute. So there you go. Okay, one last one here. And it's a nice one to finish up on because it's again going to go over some similar triangles. Now before I get there with the similar triangles, let me remind you of something that maybe you're kind of unconsciously aware of, and that is you really have a better ability to calculate volumes than you may realize. So let's take a look at a couple volume figures. Let me start with a rectangular solid. So here, and all right, so I'm not really great at 3D rendering. Oh well. Length, width, height. But if you start with the area of the base, we can calculate the volume of this figure simply by multiplying, right? The volume is going to be the length times the width times this other dimension, times the height. And the same thing is true when you look at cylinders. So the volume of a cylinder is going to be the area of the base. What's the area of the base, assuming this has a radius of r? Pi r squared. So if you want the volume of a cylinder, what's the formula for the volume of a cylinder going to be? Pi r squared h. Cool. So really you're taking an area formula and multiplying it by that extra dimension. Such is the case in problem number 20 here. So a trough is 12 feet long and 3 feet across the top. Its ends are isosceles triangles with altitudes of 3 feet. What's an isosceles triangle mean? Yeah, this side and this side have equal length, and those lengths are not 3. Across the top, it's 3, but not the length of each side. That's okay. So here it is. The only thing that I don't have labeled for you is the 12 feet this way. So let's start by finding the formula for the volume. This is also another one to practice similar triangles with, so try and make the most of it. What's the area of the base of this going to be? So here's your base. We're going to multiply it by the width here, or its height, its depth, whatever you want to call it, to get the overall volume formula. How do you find the volume or the area of a triangle? Good. 1/2 base times height. Glad I didn't have to coax that out of you too much. What's the length? 12. So times 12. Okay, so 1/2 times 12 gives me 6 base times height. That's the formula for the volume. Let's work with that a little bit. Our eventual goal in this problem is to find how fast the water level is rising when the depth is 1 foot. So let's see, what information do they tell us? I'll even put it up here. Water is being pumped into the trough at 2 cubic feet per minute. On your paper, write down what that means mathematically. What does that mean? Find a way to describe that mathematically. Yeah. Maybe. Giving everyone a chance. The 1/2 times the 12 canceled and gave me the 6. 12 was the length of it. So 12 was its length that way. Okay, so of the things we know dV by dt is 2 cubic feet per minute. Eventually, we want to figure out the rate at which the water level is rising when the depth is h equals 1 foot. So h equals 1 foot. Now, the rate at which the water level is changing, how would you express that? dH by dt. So that's our ultimate goal, is to figure out dH by dt. How is that rate changing? Like the last one, we're going to calculate this. We're going to try and simplify our life by using similar triangles. So you've got the big triangle out here. And let me kind of highlight that in yellow. And then a littler triangle. Let's put that one in red. You know, I don't think that'll show up very good. Let me try a different color. Blue. There we go. Let's see if we can't fill in a few things. You know what? It might be easier, rather than using half of this, let's use the whole thing. Yeah, that'll work. Because what's the distance across the top? 3. Good. So I've got 3 feet across the top. So I'll use a 3 here and a base here. So overall, the whole thing from one side to the other is just b. And then the height. What's the height here? The height is 3. So what you're going to do is you're going to form a nice relationship between h and b using similar triangles. So here's your b, here's your h. Try and form that relationship. I'll give you a minute to work on that. fold. We need to come up with some ratios. So one ratio that we can come up with is this base here, which is 3. What's the base of my other triangle? B. I want to have a proportion that relates B and H. So what's something I can use that involves an H? Yeah, so this side here and this side here, or this height here, that should be an H. That's 3 over H, not a B. There. So 3 over B equals 3 over H. If I cross multiply, I get 3H equals 3B, or better yet, just H equals B. They're interchangeable. The height and the base are interchangeable for us in this problem. Which one of these am I going to replace in this formula? The height or the base? The base. You want to keep the height because eventually we're going to need a dH by dt term here. So let's keep the height and get rid of the base. That's going to be 6 times h, or better yet, 6h squared for the volume. We're kind of getting near the end here, so let me speed things up or help things out. dV by dt. When you differentiate, you've got to use the chain rule again. On the right hand side, it's going to be 2 times 6 is 12. H to the first power times dH by dt. I regret having that V here. Not sure why. Last but not least, let's fill in everything that we know. Solve for what we don't know. That's going to be 2 equals 12 times H. What was the height? Height was 1 times dH by dt. If I divide, I get 12 into 2 is 1/6 equals dH by dt. What units go with dH by dt? Good, feet per minute. That's it. Anything on that one kind of by way of wrap up? All right. For homework, try 1 through 29. And that's section 3.7. We'll do a few more of these next time, including some Pythagorean theorem problems.